You know that morning cup of coffee? Ever stop to think what's really going on in there? You see the steam, you smell the aroma, but underneath all that, there's this invisible force at work, a silent choreographer directing this incredible dance of energy and matter. Today, we're going to pull back that curtain and get to know this force, chemical thermodynamics, and see how it literally shapes everything.
Yeah, it literally starts right here, in something as simple as familiar as a hot cup of coffee. The heat moving from the water to the grounds, the sugar dissolving, the steam rising, it's all a perfect everyday masterclass in thermodynamics. But, and this is the really wild part, the exact same principles that explain your coffee also explain the raw power of stars, the engines that blast rockets into space, and the very chemical processes that make life itself possible. So how can one single science cover so much ground? To get our heads around it, let's just start with the name. It sounds kind of intimidating, I know, but trust me, it tells you everything you need to know.
Okay, so the word itself, coined by Lord Kelvin, is surprisingly simple. Thermodynamics literally means heat power. Therme is Greek for heat, dynamis for power. That's it. At its heart, it's the science of how energy changes, how it moves around and converts from one form to another, like the chemical energy in gas becoming the motion that moves your car.
So, why do we care? What's the point of all this? Well, thermodynamics helps us answer some of the most basic but also the most important questions about pretty much any process you can think of.
It gives us the tools to actually measure the energy involved in any change. But more importantly, and this is the really cool part, it lets us predict the future. Like, will this chemical reaction just happen all by itself? And if it does, how far is it going to go before it runs out of steam? It's basically the universe's rulebook.
And you know what? That rulebook is shockingly simple. It all boils down to two main principles that govern, well, everything. Forget complex laws for a second. Let's just call them nature's two fundamental rules.
All right, rule number one, you can't win. You can only break even. You can't just create energy out of thin air, and you can't destroy it. All you can do is change its form. Rule number two is one we all know deep down. Think about your desk or your bedroom. It doesn't tidy itself up, right? Things just get messier over time. The universe is no different. It has this powerful, natural pull towards disorder.
But that kind of begs the question, doesn't it? Why? Why is messy the default setting for the entire universe? To understand that, we need to wrap our heads around one of the most important ideas in all of science, entropy. Entropy is really just a fancy word for disorder or randomness. So picture an ice cube tray. The ice cubes are in a perfect, ordered crystal structure. That's low entropy. But what happens when it melts? You get a disorganized puddle of water molecules all over the place. That's high entropy. Same thing with a brand new iron gate versus a rusty one. It's just simple statistics. There are way more ways for things to be disordered than for them to be perfectly ordered. So what this really means is that all chemical reactions are being driven by two main desires. First, that drive we just talked about, the move towards more messiness, more entropy. And second, a drive towards lower energy. As the source material puts it so perfectly, nature loves being lazy. It always prefers to be in a low-energy, stable state whenever it can, kind of like a ball that always rolls to the bottom of a hill.
Okay, so now we know the rules of the game. Nature wants low energy and high disorder. So can we actually use these rules to predict whether a chemical reaction is going to happen on its own? The answer is a huge yes, and we owe it all to some truly brilliant minds.
Now, this wasn't some overnight breakthrough. It was built piece by piece, over decades. It started with people like Sadi Carnot, who was just trying to build a better steam engine. Then James Prescott Joule came along and proved that heat isn't some weird fluid. It's actually a form of energy. Then Rudolf Clausius gave us the math for disorder, for entropy. But the person who put all the pieces together was an American scientist named J. Willard Gibbs.
What Gibbs did was absolutely genius. He realized you had to account for both of nature's tendencies at the same time, the push for low energy and the pull towards high disorder. He combined them into a single, elegant number called Gibbs free energy. And this one number gives you the final verdict. It tells you, point blank, will this reaction go on its own or won't it? It's the ultimate decider.
So we've gone from a simple cup of coffee to the fundamental rules that run the universe. Now let's bring it all back home and see how this unseen choreographer is directing the world all around us every single day. Every single time you open your refrigerator, you are looking at a machine built on the laws of thermodynamics. It's using energy to literally fight against nature, to pump heat from a cold place into a warmer one, which is the exact opposite of what wants to happen naturally. It's a direct manipulation of these rules.
Now let's just scale that idea way, way up. The very same rules that are keeping your milk from spoiling are harnessed to control the absolute chaos inside a rocket nozzle, converting chemical energy into the immense power you need to break free from Earth's gravity.
And the applications just get more and more mind-blowing. Understanding how molecules are going to interact, how proteins will fold into the right shape, whether a drug will actually bind to its target inside your body, all of this comes down to chemical thermodynamics. It allows us to design medicines with breathtaking precision.
What this all means is that thermodynamics isn't some dusty old science from a history book. It is a universal language, and it is absolutely central to solving our biggest challenges today, from finding new sources of sustainable energy and fighting climate change, to building faster computers and creating new breakthroughs in biotech.
From the steam in your coffee cup to the engines of the cosmos, thermodynamics is the quiet, powerful force riding the rules for everything. It choreographed the world we live in, and it will, without a doubt, choreograph the world of tomorrow. The only real question is, what will this invisible force help us create next?